Yeah, I'm actually filling in for Slater Victorov today, our CTO. I'm at Indico Data Solutions, so I'm just going to be your budget Slater Victorov for this morning. So first, kind of want to introduce some of the basic motivation of why even we would care about text embeddings and why even we would care about transfer learning and training models to solve downstream tasks using text embeddings. This is a thing we've seen over and over again at Indico, is that everyone has problems, everyone has data. It's a real problem, and oftentimes to gather the right data, you need domain expertise. Because of this, small data problems are much more common than big data problems. And for the purposes of this talk, we're going to talk about small data problems as being anything less than about 1,000 examples. So let's jump right in. Let's talk about transfer learning. First of all, what is it? Transfer learning is the application of knowledge gained in one context to a different context. You can talk about transfer learning in the context of human transfer learning. This is something we do all the time. We take some skill we've gained in the past and we apply some of the same moves to learn something new. But it's also something that you can do in the machine learning community as well. This is just a picture of a tiger. It's actually also an analogy. So we're going to talk about the way in which you understand what a tiger is. So one potential way you might represent what makes up a tiger is you could represent it as its pixels. So we have our kind of shuffled tiger on the screen. And you can see that we have each pixel is independently predictive of whether or not this image constitutes a tiger. Because you can, look at this pixel right here we have highlighted in blue and say, hey, it's orange. Maybe this is a tiger. Or hey, it's black. There's a high normal likelihood that this thing that we have might, in fact, be a tiger. But it's a pretty lossy representation. And it's pretty difficult to learn to relate all of these pixels together in order to form the conclusion that what we've got on our hands might just be a large cat. And so because of this, it would be really handy if we could represent this tiger in a better way. This is kind of where transfer learning, and in particular, learned representations of data come in. So if we could instead represent this as a large orange striped cat and various activations for each of those features, it'd be much easier to tell that the thing we've got on our hands is in fact a tiger. This is something that a small child might learn to do. If this is the first time they've ever seen the world, then it might be very difficult to put together what their eyes are taking in. But if they already have knowledge of what a house cat is, what stripes are, what size is, and what the color orange is, they can pretty easily put two and two together. So this is what transfer learning looks like in a machine learning context. Here on the left-hand side, we have what we call our shared encoder, or our featurizer. In this case, it might be a model trained on something like, let's say, movie review sentiment. On the right-hand side, we have a custom classifier, which we call our target model. We actually have a couple of them. Each of these arrows represents a different model that's been trained using the features extracted by this source model. So, we might modify the model to do movie genre prediction, or movie sentiment aspect, or predict box office results. So in general, the formula for transfer learning is to train a base model on a very large generic corpus. We're going to take the way in which the base model represents its input data and use that representation, the output of this little triangle here, as the pre-trained feature representation for a custom task. So let's talk about pre-trained embeddings, and in particular, pre-trained embeddings for natural language processing tasks. Again, why should we care? Well, first off, text is super sparse, and you simply might not see a word. If your representation for your data is whether or not each individual word occurred, if you see a word in your test data that doesn't occur in your training data, you're out of luck. You just have no idea what you can whether or not this particular word is associated with a positive or a negative result. Secondly, learning good representations requires large amounts of training data, and data is expensive to acquire. So it'd be nice if we could kind of have this already from the get-go when we go to solve a custom natural language processing task. When we do learn word representations, we find that they have some interesting properties. So if you're part of the natural language processing community, you've probably seen this diagram before, but it's a popular one because it's a very interesting property of word representations. You take the word vector for the term king, and you subtract the word vector for the word man, and you add the word vector for the word woman, you end up with something that approximates the word for queen. So you can see that these learned representations of text have encoded something semantically meaningful about what these terms represent. This is actually from a paper, I think in 2012, by these folks down here. And there's a whole library of options you have for representing text. So you have word2vect, that was the last slide. You have something called glove, which represents words by computing some statistics about what words co-occur in a document and what words occur close to words in a document. And you have this thing called ELMO, which stands for Embedding Language Model, by the Allen AI Institute. In general, I'm just going to ask you to trust me that if you want word vectors that are fast, use glove. If you want word vectors that are accurate, use ELMO. So let's actually dig into ELMO and talk a little bit more about what is going on behind the scenes. ELMO is from a paper called Deep Contextualized Word Representations. And it uses the outputs of a 3-layer LSTM, bidirectional LSTM, as representations of words. And this LSTM is trained to predict the next word on a large unsupervised corpus. This is a language modeling task. And then these learned word representations tend to contain important information about word context. So let's use the word bass or bass for an example. If you only learn the representation for an individual word, and the word has multiple meanings in different contexts, then the word vector for that word is going to have to encode all of those different meanings at once. So this means that BASS has to represent the fish, it has to represent the low tones, it has to represent bass guitar. So it's kind of confusing, and it's hard to keep all these varied meanings in a single word vector. So ELMO deals with this by incorporating contextual information into the representation. Yeah. Thanks. I'm sure that was painful. Sorry about that. And this is quickly... We good to go? Yeah, there we are. And it's quickly becoming a standard in academia and industry. So what is this language modeling task I was talking about? It looks something like this. So if you have the sentence, I thought I would arrive on time, but I ended up 5 minutes blank, we as humans can say, obviously the word late occurs here. But in teaching a machine learning model to solve the same task, we learn meaningful representations of language. So it's this next word style prediction objective. So I've given you like really brief high-level overview of what learning representations for text looks like. So let's talk about solving downstream tasks and the kind of things we need to care about if we want to train a machine learning model without a lot of labeled training data. Before we go to the words, let's look at the photos here. It might be a little hard to see. But here on the top left-hand corner, we have some random data points that we've just kind of thrown on a chart. If we use a very complicated machine learning model, and we have a lot of parameters, and we only penalize how well the model performs on the training data, we might get a result like we see on the top right-hand side. And this is an example of overfitting. So the model has learned to exactly go through every single one of our data points to minimize error. But as you can see, in fact, it's learned pretty much nothing at all. So it's overfit very heavily to our training data. And a model like this really isn't useful, because if we'd have a point, say, here in our test data, and we'd expect a result like this, we might get a very unexpected output. Our model has not learned to generalize. And you can see this here in the bottom left. But if instead you use a very simple machine learning model, or you penalize the model learning complex functions, you instead get the expected result, which looks something like a straight line through your data points. This might not be optimal, but it definitely generalizes. And if your test data doesn't look like your training data, it's very important that your model generalizes. Often a go-to for training a target model is logistic regression. That actually goes a very long way because it's a rather simple method with not a lot of learned parameters. So it's hard for it to overfit. We often also use L2 regularization, which is a penalty on learning large weights, because large weights often correspond to the model being overconfident in a single feature being predictive of an outcome. Or dropout also works. Yeah, so for stuff like document classification and regression, things like linear regression, logistic regression can work, but we don't even know how to represent our inputs for more complicated tasks like comparing a job description and a resume, or labeling all of the terms in a sequence by their part of a speech, or by whether or not they represent a named entity like DSS Miami. So we have to get a little bit more creative. First, we're going to talk about that second one, this sequence labeling task. As I said before, named entity recognition is an example of a task like this, where you read over some text and you learn to identify whether or not something is a proper noun. And here I'm going to introduce something called temporal convolutional networks. So this is one option we have if we want to label every single word in a sequence. We're going to represent our input, our words, as an array of word vectors that come out of one of our pre-trained embeddings, like glove or Elmo. And then we're going to apply some convolutions on top of those words. A couple layers of convolutions, and we'll eventually get an output. So I'm going to break this down and kind of dig into each of the factors that makes this a good choice for predicting the label for each word. This is what normal convolution looks like. So if you want to make a decision about the word that occurs here, we have some layers of convolutions, and that word gets as input context that extends to about 5 words back, which is kind of problematic, because it means that you need a lot of convolutions in order to get more context than about 5 words. So you have this unfortunate property if you say want to solve a task like predicting which speaker uttered a given paragraph. You might want to look in a book, for instance, and see, find the line that says, said Dan, and then you can predict who said that line. But if you only have 5 words of context, that's problematic. And it's expensive to add more convolutions because that takes a lot of parameters. And it means we're less likely to be able to learn a generalizable model. So we're kind of at we are ourselves a situation here. The alternative, this is actually for a model called WaveNet, but the same principle holds, is to dilate our convolutions, which means space them out by increasingly large intervals over time. So now, this single prediction at this word is able to take into account a much larger area of context that goes back about 16 terms, or 2 to the 4 terms, since there's 4 layers of convolution in this model. So now we've kind of given the model the capacity to see a much larger area when it makes a decision. I want to introduce another concept called a residual block. So I said previously that model complexity is one of the most limiting factors for learning a machine learning model without a lot of labeled training data. And model complexity is not just a measure of the number of parameters in a machine learning model. It's also a measure of the distance between input and output. So if the mapping between an input and its prediction is complicated and is the result of the application of a bunch of functions in a row, like chaining functions together, like an RNN, for instance, to get that information from the first state, you need to propagate it through all of the subsequent states in order to produce an output. It can be hard to learn the relationship between the input and the output because of that complicated mess in the middle. So what residuals do is you simply directly add the input to the output of a operational block. And this means that the relationship between your input and your output is much shallower. It's much less complex. There's not a lot of crap in the middle that you have to backpropagate through. And this, as an analogy, you can kind of think about how a painter might paint a painting. When you start painting a painting, you kind of want to start in broad strokes. You're not going to find one corner of the painting and just make it in intricate detail and then do the same thing as you move across the image. That's not really how it works. You lay down the background, you give it some very broad strokes, and eventually fill in the details. And that's kind of what's happening here. So you start by giving the model access to very simple information, the representation of the input. And the model learns to associate the inputs with an output in much the same way as logistic regression works. But over time, the model can also learn to use this more complicated mapping, which in this case is a series of convolutions. So this residual is integral in making sure that can occur. Let's talk about our other example, which we had was comparing a job description and a resume. If you're a member of the deep learning community, you've probably heard that feature engineering is bad. We should always learn our representations. And to a certain extent, that's true. But I think feature engineering still has its place. It just has a different form. I believe that feature engineering takes the form of model architecture decisions that you make in a modern deep learning context. So in deciding how we represent our input, we decide how we architect our model. So for instance, a good feature might be to compare the representation of the job description and the resume, subtract those two vectors to produce a model input. And for the task of deciding whether or not two sentences contradict or agree with each other, Facebook decided on this representation for their in-1% paper. So they feed the model U, which is a vector representing the job description, V, which is a vector representing the resume, the absolute difference of the two, U minus V, and the element-wise multiplication of U and V. So these are rough measures of similarity that the model can use. And because we've given the model some prior about how we think the world works and how we think this particular problem works, the mapping between input and output is simpler. We've taken some of the burden off of the model to learn a complex relationship between the input and the output, and we've put it onto the machine learning architect making the modeling decisions. And this is incredibly useful when you don't have a lot of data, and it's almost necessary. So in conclusion, small data problems are much more common than big data problems. The pre-trained embeddings you use matter, and you should search for the simplest possible target model for the problem. That's all I got for you today, but happy to take questions or something.